Okay, so the last Leetcode practice question for today. So two goes. The first one still is to find the solution and put in some solid code after that, and the second one is to see how to solve this problem properly during an interview. So in the interview, usually the first step is to understand the question and clarify, and of course you need to think about the edge cases. So let's give it a shot. So let's say vertical order traversal of a binary tree. Okay, so given a root of a binary tree, calculate the vertical order traversal of the binary tree. For each node at position xy, its left and right children will be at positions x minus y and y minus 1. Sorry, x minus 1 and y minus 1. And x plus 1, y minus 1, respectively. And the vertical order traversal of the binary tree is a list of non-empty reports for each unique x coordinate from left to right. So each report is a list of all nodes at a given x coordinate. And the report should be primarily sorted by y coordinate from highest y coordinate to lowest. If any nodes have the same y coordinate in the report, then the node with a smaller value should appear earlier. Okay, so return the vertical traversal of the binary tree. I think I kind of get it. Let's take a look at the example. Let's just directly see the second example, which is more complex. So it's going to return first list as 4, like this column, and then 2, this column, 5, okay, 1, 5, 6, which is this column. So 5, 6, it has the same, so 5 and 6 is on the same column and same row as well. And then 3 and then 7, okay? So let's see some constraints. Let's say node is node value between 0 to 1000, and the number of nodes in the tree is in the range of 1 to 1000. So edge case not exists because the tree is not going to be empty. So the root is not going to be a non-pointer. So the next thing is about finding a solution. So I would say in this one, we could do a BFS, and for each node, except for the tree node itself, we are also going to keep track of the coordinate, which is x and y. And after the BFS, we are going to, so during the BFS, we are going to when we traverse the root, when we traverse the tree, we are going to store the things into a data structure, something like this. So the key is the integer, which is the column, and so which is a column, and the value would be another I would say it could be an array, and the array is a pair, and the pair contains the x-axis. So the pair first it's a integer, and the second one is also integer. So the first integer represents which row it is currently in, and the second one represents the corresponding value. So for example, for this root node, so we are going to put okay, so both x and y are 0, so it's definitely going to be map 0 and 0. Okay, so it's an array. So this one definitely is stored at map 0, and and the corresponding pair would be something like 0 and 1. So something like that in this array. So let's see what would be the runtime for this approach. So essentially for the BFS, the runtime is going to be O of n, and then since it asks us to return a sorted list, then we need to sort each column correspondingly. So each column, actually the size of each column is quite different. I would say in the middle it will have more number, but yeah, I think it's not very clear how many nodes are there. So supposedly the longest, so the column that contains the most nodes, it has m nodes, then the sorting is going to m log m. So how many columns are there? Okay, so I think one way to like get a rough estimation is not like an exact one. Let's say we have k columns, and we have the n nodes, and suppose we have m columns and n nodes in total. Suppose the nodes are distributed evenly in different columns, which is not true, but it's just a rough estimation. So to sort each of them, it's going to be m divided by n and log m divided by n, and we have so it is n divided by m and then n divided by m, and so since we have m columns to be sorted, then we times m, so it is going to be n log m divided by m. So this would be the general time complexity. As I said, it's just going to be a very rough one, because we don't know like the distribution of the nodes, like the distribution of how many nodes on each column. So it's not very exact thing. So after we find the solution, the next part is about doing some coding work. So for the coding part, speed, the correctness, and also the readability. That's the three things we mainly cared about in the coding part. So let's start to do some coding work. Okay, so BFS, so first of all, we are going to define a queue. So the queue will have the tree nodes, and okay, so the tree node is not actually enough, because we still need to know. Okay, so let's say you just say define a class. Let's say class node. So it is going to have several different things. The first one is going to have a tree node with let's say just node, and also we will have the integer x. Let's say we just call it row, and we also have the integer column. So let's say we give it a constructor. Let's say it is public node, node and row, and call. So this dot node is equal to node. This dot row is equal to row. This dot call is equal to call. Okay. So that's it. So actually for this queue, we are going to keep the nodes in the queue. So let's say it is queue, and the new we use linked list as a underlying implementation. And first of all, we are going to of course add a root into it. And okay, so well, q is not equal to none, and then that's the body of BFS. So the purpose of this BFS is actually to store the nodes into the data structure defined on line 10. So actually it is map integer and the value is gonna be array, so it will be pair of integer, let's say it's just pair. Okay, so let's define another thing which is called pair. Okay, so it has two things. The first one is of course the y-axis. Okay, so we have two things. The first one is it's actually the row number. Okay, so let's say row number, and the other one is actually the value of the tree node. Let's say it is a value. So give it a constructor. Let's say public pair row value. Okay, this dot row is equal to row, and this dot value is equal to value. Okay, so let's read this one again. So this should be primarily sorted by y current from the highest. From if two nodes have the same y current in the report, then the node with the smallest one. Okay, with a smaller one. Okay, so okay, so I think we are still good. So first of all, we are going to put the q into it. Okay, so it is this pair, and I would say it is column. It's column. Let's say column row map is new row value map as new hash map. Okay, so first of all, let's say I size, so int size is equal to key dot size. Okay, so we are not going to add a root. My brain is not clear at this moment. It should be root. It should be the new defined node data structure, which is node and let's say 0 and 0. Okay, so dot size, and we are going to iterate through the current layer. So 0, I smaller than size, and plus plus I. So the node is equal to q dot pop. Okay, so it's full. Okay, and int, let's say row, would be equal to node dot row, and call would be node dot call, and we are going to say okay, if column row map that contains key. If it doesn't contain column row column row value map. If it doesn't contain the key, which is a column, then we are going to put a new array. Okay, so this should be a let's say it should be a list. Okay, so let's say, so we are going to say, okay, we are going to insert a new list into it. Then column row val map dot put the column number and also the new, let's say it is maybe array list, sorting it. So array list of the pairs. Okay, and then column row value map dot okay, so dot get call dot add a new pair, which is the row number and also the corresponding value. So let's say, okay, we haven't defined a value. Okay, so it should be node dot value. Okay, and the next thing is, if the left child node dot node, okay, it's a node dot value. Okay, the node dot left is not equal to a non-pointer. Yes, if it's not equal to a non-pointer, so what we are going to do is we are going to push the queue dot add the new node. So it's gonna be node dot left, and also the row column. So the row, so it's left tree, so the column would be to column -1, a row would be row -1. Okay, and then same here. So for the right child, if node dot right is not equal to a non-pointer, then we add it. So now node, it's node dot right. Okay, so it is row -1 column +1. All right, so as we go through this, we are going to construct this one, construct a column row value map. So the next thing for us is to actually why, so this one is BFS traversing, and this part is actually about sorting. So why it works like this, it doesn't make sense. Oh, so maybe I'm losing something here. So this is a if, this is a if, this is a if. Am I missing some bracket somewhere? Okay, what is happening? So this one is matching, so this one is matching this one. How should there be something else? Yeah, it's weird. Okay, so this one is matching this well, so it should essentially be this one. Yeah, so it is this one, and This is a if. This is a if. New pair. I'm not getting it. So I'll put this line inside. I'll put all the things inside of it, right? And then why it is still, I think, yeah, I'm looking this bracket here. Yeah, that's essentially why. Sorry. Now it should be good. Okay, so the next thing is about sorting. So you're going to say, okay, so at the same time during this visit we need to record the max column number and the min column number. So let's say we have the max call defined as 0 and the min call defined as 0 as well. So max call is equal to max, which is call max call main call is equal to max dot main call and main call. Okay, yeah. So then we need to do the sorting. So we are going to go through from the main call to the max call. So call is equal to main call, and call is smaller equal to max call, and the plus call. All right. So for each of the lists, we need to sort them. So list, okay, so it should be collections dot sort the pair. Okay, sort, I would say it is column row value. Okay, value map dot get the column. So getting the corresponding column is going to return the list, and then you will say new comparator pair. So new comparator pair. So let's say how to Java comparator. Okay, so Java comparator, we need to implement okay, so compare. Okay, override compare. At override int compare. So okay, so it's this one. So pair P1, pair, and P2. So we need to sort first by the row number. So if the row number is the same, so if row is equal to P2 dot row, then we are just going to return sort based on the value. So return P1 dot value minus P2 dot value. Otherwise, what we are going to do is we are going to return P1 dot row minus P2 dot row minus. Oh, actually not. So it is P2 dot row minus P1 dot row, because max row comes first. Okay, And then after sorting, after we sort it, so let's see what is okay. It asks us to return a list of list. So list of list integer. This is the how to call it. So it's vertical outer traversal. So just for the simplicity, let's call it a list of the list. Let's say we return a linked list. Yeah. And so linked list integer one column new. Sorry. This one should be list new linked list. Okay. And then for okay, so for integer, actually it should be the pair. Okay, pair p from column row value map dot get column. Okay, so we are going to go through that, and one column dot add p dot value. Okay, then we put dot add. We are going to add it into the return thing. So we are going to say one call, and finally we return ID. So that will be pretty much about the code. Let's do some testing on top of it. So for the testing part, usually you go through a test case, explain how it works manually, and then try to set up some other test cases to increase the test coverage. So let's say we define a class, tree node, row and column, okay, and the pair define row and value, okay. So let's see this example. Let's take this tree. So first of all, it is going to be root. Let's see the BFS part. Before that, we define a integer to a list of pair. Key is the column, and the value is the pair. Pair contains the row and value. Okay. So we put the node here into it, the root node into it, max and min column, and then we are going to BFS the queue size for it, and we are going to go through each layer. Okay, this should be queue if queue is not equal empty. So if it's not empty, so while queue is not empty, then we are going to do that. So well, queue is not equal is not empty, and we are going to go through that. Yes. So as equals smaller than size plus this is for this layer, and so node pop the first node, and then get the corresponding row, column, and the corresponding value. Set this one, okay, and then if it is if it doesn't contain the corresponding column, we put a new thing into it, and then we add the pair into it. Okay, so if the left child is not a non-pointer, then the corresponding column number is col -1, and the row -1. Okay, otherwise it should be column +1. Okay, so this looks to be correct. Okay, then after that we have this data structure which contains so now the data structure would look like something. So now the data structure would be something like let me put it here. It would be something like okay, it will be something like it has, like for this specific tree, it's going to be -1 with a 9, and so it is with a pair of -1 and 9. Then it has 0 in it, and so the 0, it will have the 0, 3, and the other thing is what is that? So it is minus, so it is actually the row number is -2 and the 15. Then the other thing is the 20. Sorry, it is 1. So key is 1, which is a column number, and also it will have 1 and 20. Okay, and then the next thing, it would be 2, and it will contain the 2 and 20. Okay, then we sort each of them first of all based on this the row number from the largest to the smallest, and then if the row number is the same, then we sort the corresponding value from okay, so if the row number is the same, then we sort the corresponding value from the smallest to the largest. Okay, yeah, I think it looks good. Let's give it a shot. So okay, so compare row, not surprisingly, so new node. Okay, so it's called root. So int compare, so compare in anonymous solution cannot implement compare in comparator. Compare solution dot pair what is it saying? So anonymous solution cannot implement compare tt in comparator. Compare solution. Okay, so let's see. It is complaining about this part, I think. It's complaining the comparator implementation cannot implement can't implement in comparator. I don't really understand. So it's a new comparator. Let's see. Oh, I think I forgot that. No name must comparator. Am I doing it wrong? So let's see. Sort this new comparator. I think it's pretty much the same. Public int. Okay, so it's public int, maybe. I missed that. Okay, so now it's good. Oh, I missed the public, sorry. Let's give it a submission. Okay, so it's accepted. So then that's it for this coding question. As I said, when we set up the task case, I would say not too much. I would say maybe just either example 1 or example 2, both are fine, because there is not too much edge case to think about. It should be good enough for either the task case to cover pretty much most of the branches. So that's it for this coding interview. I hope you find it a bit helpful, and thanks for watching this video. Have a good night.